Hi there. Welcome to another online video lesson intended to provide you important principles and helpful tips for the study and practice of argumentation. This is the third in a series of videos looking at argument prototypes. In this video, we're going to look at the substantive warrant prototype known as generalization. We're going to get a sense of how generalization reasoning operates, how those warrants tend to connect data to a claim, and then along the way, we're going to get some practice both analyzing examples of generalization arguments, as well as applying tests for evaluating these warrants. How do we know if a generalization is being used in a way that's logically reasonable, as opposed to the deployment of a fallacy? But first, we need to remind ourselves of an important concept from our last video. What do we mean when we say that generalization is a substantive warrant prototype? In a substantive warrant, an argument may carry data to claim by means of an assumption concerning the relationship existing among phenomena in the external world. And these connections, these specific types of relationships, while in practice are nearly infinite, can really be boiled down to a handful of typical moves, typical kinds of connections or relationships that we see over and over again. So for instance, in part 2 of this series, we took a look at argument from cause and argument from sign, very typical approaches to substantive reasoning. Argument from generalization. According to Brock, Reedy, and Enninger, in an argument from generalization, the warrant assumes that what is true of the items constituting the sample in the data will also be true of members of the class not represented in the sample. Inch and Tudor provide an alternate definition that's pretty simple to understand. In an argument from generalization, according to Inch and Tudor, what is true of certain members of a class will also be true of other members of the same class or of the class as a whole. This type of reasoning is what's often referred to as induction or inductive reasoning. This is the kind of reasoning that often gets used, for instance, in the scientific method when you're first trying to get a sense of what phenomena are worthy of study such that you can ultimately construct a hypothesis and subsequent experiments on it. I did a little bit of amateur naturalism in the place where I used to live in the state of Illinois. Let me tell you about it. For nearly 15 years, I lived in a region of Illinois referred to as the Quad Cities in the northeastern part of the state, right on the Mississippi River. And when I started living and working in the Quad Cities, I noticed something a little odd about the local wildlife. One of the first days I was there, I saw a black squirrel, and that seemed kind of weird to me because most of the squirrels I had ever seen in my life were brown, and so this was something a little bit odd. But then a little bit later that day, I saw another black squirrel, and that seemed even more odd to me because black squirrels are pretty rare, at least in my experience in the state. So I continued to observe these squirrels on the campus where I taught and in local parks and elsewhere. And I would see squirrels. There's a black squirrel. There's a black squirrel. Oh, there's a brown squirrel. There's another black squirrel and another black squirrel. Oh, a brown squirrel. Neat. And another black squirrel. Now, this seemed really odd to me because throughout my entire life living in other parts of the state of Illinois, I've lived near Chicago, I've lived near Champaign-Urbana, I've lived in the west central part of the state, and generally when I've been observing squirrels, they have been overwhelmingly brown. Occasionally a black squirrel, but otherwise we're going to get these brown squirrels. Or maybe technically they're red squirrels, I don't know. Anyway, they look like this, they don't look like this. So, what's going on here? Well, I was able to ultimately come to a conclusion through inductive reasoning about the population of black squirrels in the Quad Cities. And how might I map this out in a Toulmin diagram? Well, here's my data. In the Quad City area, my squirrel sample was approximately 70% black squirrels, 30% brown squirrels. However, in other places in the state of Illinois, 85% of the squirrels were brown and 15% of the squirrels were black. Now, bear in mind, I haven't counted every single squirrel in the state of Illinois. That would make me a very strange person indeed. So this is just a sample. This is a part of the larger population. But from this sample, I draw a conclusion that the black squirrel population in the Quad Cities area is about 55% higher than that of Illinois as a whole. Now, how do I get to this conclusion? Because I'm using a generalization warrant, inductive reasoning. What's true for the samples that I observed is generally true for the squirrel populations in these areas. What's basically going on in inductive reasoning or argument from generalization is a process like this. We have a complete population. a class, a set of similar things. In this case, I was looking at the class of squirrels in the Quad City area as part of my argument, and then I looked at the larger class of squirrels in the entire state of Illinois as another class, another set of similar things. And so within any class, we're going to find an example, a member of that class, or we may find a sample, a number of examples that are all part of that class of similar things that we're aggregating. The way that inductive argument, or argument from generalization, operates is what's true for an example or sample of the class is going to be true for the entire class as a whole. So this is how I got from the sample of squirrels that I personally observed to making a broader generalization about the squirrels in the Quad Cities completely, as well as the claim that I made about the squirrels in the entire state of Illinois. Now, this is just some silly amateur naturalism, but inductive argument, argument from generalization, is used all the time in public policy argument. For instance, in public opinion polling. Here's an example of a report that was presented by the Gallup organization on May 31st, 2019. The conclusion of the study is that Americans are saying that U.S. moral values are not good and actually getting worse. And in the report, they make claims about what Americans say overall based on a sample of U.S. citizens and residents that they're able to poll. So how does that work in this study? Well, we've got some data. According to a poll that was taken between May 1st and May 12th of 2019, they found that when asked, what do you think the current state of moral values in the nation is, 47% of the sample reported poor, 36% reported fair, and only 17% reported either excellent or good. So based on this sample, they drew the conclusion that Americans say U.S. moral values are not good. And the implicit warrant that makes this argument work is that what's true for the poll sample is generally true for the U.S. population. This particular warrant is implicit. It's not specifically stated in the report. But what they do specifically provide in the report is some backing for this warrant. Why is this warrant reasonable? They provide discussion of their methodology, and they specifically describe how the study involves a validated random sample of 1,009 adults with a margin of error of plus or minus 4 points and 95% confidence. Now, in terms of statistics from a social scientific perspective, 95% confidence is really, really good. So the numbers are potentially a little bit off, plus or minus 4 points, but on balance, this is a really sound statistical sample, leading to a conclusion that's reasonably accurate. This is how good public opinion polls operate. So you'll notice that we're moving from a sample of the larger population to draw a conclusion about the population as a whole. Notice, in order to do that, what we're going to need is what statisticians refer to as a representative sample. So if I wanted to conduct my own poll on American public opinion regarding moral values in the nation, I wouldn't necessarily be able to go into a specific church, for instance, and ask everybody that is having lunch after the service, hey, what do you think about the moral values in this nation? I would have a really good sense of what the overall public opinion is on moral values in the nation for that church population, but the people who go to that specific church aren't necessarily going to be a cross-section, aren't going to be a representative sample of U.S. citizens and residents as a whole. What I would need to do is what these professional polling organizations do and develop methodologies to determine how do we get a sample of Americans that really reflects the larger population as a whole in its diversity. If I have a representative sample, I'm in a good position to make a good generalization argument. If I don't have a representative sample, not so much. So if I'm going to evaluate a generalization argument like this, how do I go about doing it? Well, let's go to the 3 types of tests that we've been talking about in this series to see how they would apply in a generalization argument. The test of quality, or whether or not there's a relevant relationship between data and claim. Are the sampled observations, or is the example being provided, relevant to the general claim? Is there a connection between them that makes sense? Test of quantity. Are the sampled observations, or is the example, sufficient in number to support the general claim? Do I have enough examples or enough observations in order to make my inductive leap? And finally, the test of opposition. Are there counterexamples that make the generalization to the entire class unreasonable? In the case of a well-designed public opinion poll, the test of quality is going to pan out if my sample is going to be a relevant picture of Americans as a whole, which is the claim that I'm making in the poll. And so if I have a representative cross-section sample of U.S. citizens and residents, then yes, that's going to provide a relevant picture that enables me to justify my claim about what all U.S. citizens and residents believe. In the test of quantity, social scientific pollsters have very specific methodologies that determine how many people of different types in a random sample you actually have to poll in order to be able to make a generalization that's statistically defensible. And so in the case of the poll that Gallup does, 95% confidence, it's pretty good. Test of opposition, are there counterexamples that make the generalization to the entire class unreasonable? Well, yes, because we've got that 17% of Americans that think that moral values are either excellent or good. And so in the argument that's being presented by Gallup, well, that's being presented as part of the qualifier and the rebuttal. The vast majority of Americans believe that moral values in the country are not good, but there is a small minority that does think so. Now, for an example of a generalization argument that is rather less logically sound, let's go to the presidential campaign announcement address of Donald Trump on June 16, 2015. In this speech, as many of you may be aware, President Trump made a rather dramatic claim regarding the character of folks who immigrate to the United States from Mexico, either as an undocumented immigrant or perhaps even as a legal immigrant with a visa. He didn't make that distinction in the argument. Let's remind ourselves what he said at that point.
The U.S. has become a dumping ground for everybody else's problems. Thank you. It's true. And these are the best and the finest. When Mexico sends its people, they're not sending their best. They're not sending you. They're not sending you. They're sending people that have lots of problems, and they're bringing those problems with us. They're bringing drugs, they're bringing crime, they're rapists, and some, I assume, are good people. But I speak to border guards, and they tell us what we're getting. And it only makes common sense. It only makes common sense.
Okay, now let's use a Toulmin diagram to analyze the argument that Trump's making. He makes a claim that Mexican immigrants are criminals, and he provides some pretty dramatic and derogatory details to describe the kind of violent crime that he's talking about. Later on in the argument, part of the argument that generally didn't make the sound bites that were used in the news, that he's had conversations with some border guards, and the border guards are telling him, this is what we're getting. This generalization then depends on the following implicit warrant. What's true from anecdotal reports from these border guards is generally true about the people that are coming to the United States from Mexico. And he does provide an additional sort of backing for the warrant very late in the argument where he says it only makes common sense. So we have a sense of the generalization that then candidate Trump made about Mexican immigrants coming into the United States. Let's run our tests of generalization warrant. Test of quality. Are the sampled observations relevant to the general claim? Now, in this specific context, it might be reasonable to suggest that border guards have an opportunity to observe the kinds of folks that are coming over the border from Mexico, but we don't know necessarily who these border guards were, what particular points of the border that they're guarding, whether or not they're just observing the people that are coming over the border at regular points of entry, whether they're border guards that work specifically on investigating and apprehending undocumented immigrants. We just don't know. We don't know who any of these people are. We don't have any source citations or sense of the specific jobs that they do as border guards. So the quality of the information in order to make a general claim about all Mexicans who come into the United States over the border, it's really difficult to make this connection because we just don't know which Mexicans these particular border guards are observing. It may be accurate, it may be completely unfair. Similarly, the test of quantity. Are the sampled observations sufficient in number to support the general claim? And the short answer is, we just don't know. We don't know how many people these border guards observed, and we don't know how many people those border guards observed relative to the overall number of folks who come across the border from Mexico into the United States. And we don't know whether or not the people that these border guards observed is a representative cross-section of that population. It could be a very small and very atypical type of person that's coming over the border that these border guards are observing. So we just don't know based on the information that Trump is providing in the argument. Finally, the test of opposition. Are there counterexamples that make the generalization to the entire class unreasonable? Well, yes, that's the case, and Trump himself allows for this at the end of this infamous soundbite. He provides an implicit qualifier of most Mexican immigrants being criminals rather than all Mexican immigrants being criminals because he does provide an explicit rebuttal. Some, I assume, are good people. So note what he's doing here is he's using the explicit rebuttal and the implicit qualifier to come down from an absolute 100% generalization that Mexican immigrants are criminals. He's basically making an argument. Most of them are criminals. Some, I assume, are good people. However, even then, there's a significant problem with the tests of quantity and the test of opposition, in that statistical information tells us pretty blatantly that the overwhelming majority of people who come into the United States from Mexico are not, in fact, criminals. And so, given that glaring distinction between the shaky basis on which this generalization is being made, as opposed to the empirical evidence that we have about most Mexican immigrants most of the time, we can identify this argument as committing a specific and typical form of fallacy in generalization arguments. The hasty generalization. A hasty generalization, in brief, is a claim about an entire class based on an insufficient example or sample. Trump is painting with an amazingly broad brush about the way that most Mexicans who come into the United States are criminals, when in fact there are very few, if any, examples of that being the case, and those examples are really atypical and not really representative of the Mexican immigrant, generally speaking. So, in brief, that's how a generalization argument operates, and these are the kinds of critical questions you want to ask to determine whether or not that generalization warrant is being used reasonably. To test a generalization warrant for quality, what we want to ask ourselves is, are the sampled observations, or in some cases, is the single example that's being used to prove the claim, relevant to the general claim? That means we need to be sure that the sample or the example are in the same class as the class of things that's being described in the claim, and we want to be sure that the example or the sample is representative. In other words, does it resemble all of the rest of the items in the class as accurately as possible? When we want to test a generalization warrant for quantity, what we have to do is ask, are the sampled observations or are the examples that are provided sufficient in number to support the general claim? Do we have enough to go on, or are we possibly at risk of engaging in a hasty generalization fallacy? And finally, when we want to test a generalization warrant for opposition, we have to ask ourselves if there are counterexamples that make the generalization between the example or sample to the entire class unreasonable. Okay, so that's generalization warrants. If you have any additional questions about how generalization arguments work, any questions about the examples we talked about in the video, or in general about how we analyze and evaluate arguments using these tests of reasoning, please don't hesitate to reach out and let me know. Otherwise, when I see you next time, we're going to look at the photonegative, if you will, of generalization reasoning. Argument from classification, otherwise known as deductive reasoning. I'll see you next time.